Hi, I'm Cassie, and I'm going to walk you through question 36 of the AAMC's official physics question pack. So there's sort of a short answer to this question, and then there's a really long explanation I can give. So I'm going to start with the short explanation. Essentially, what we're trying to see here is where is the maximum electrical potential energy occurring? Is it occurring when our electrons are directly lined up on top of our positive ions? Or is it occurring when our sea of electrons moves to the left or to the right of our positive ions? In determining where that max potential electrical energy is, we need to remember, first of all, what is potential energy? And to understand what potential energy is, you have to first understand what work is. Remember that work is just a force applied over a distance. So that's a very important equation to have in your deck for the MCAT. And remember, sometimes if that force is applied at an angle, you would add a cosine theta onto here. But for our purposes, we're not going to worry about that cosine theta here. We're just going to talk about work in general. Okay, so work is force applied at a distance. So whenever you do work on a system, that work has to go somewhere. That effort you put in, it's got to go somewhere. Energy is conserved, right? Energy is not created or destroyed. So what happens when you do work on a system is that work gets converted into potential energy. And that potential energy is just stored energy that can be used later. So in the case of electrical potential energy, the work that we're going to be doing is moving charges against a charge gradient. So the short answer to this question is that if to get electrical potential energy, you have to do work, then the more work that's getting done, the more electrical potential energy we have. So in the case of A and C, where our electron C has been displaced either to the left or to the right of our ions, there we definitely have distance, a force being applied over a distance of those electrons moving. But in the case of B, where the electron C is directly lined up on top of our positive ion, that was already our sort of case zero, our equilibrium state. So we might have forces at play, but there's no distance at play. Those charged particles, those electrons, they haven't been moved. They're just staying still. So because of that, our work done is zero, whereas the work done in A and C is going to be positive amount. So our answer here is going to be that our maximum displacement happens at answer choices A and answer choice C. Now let's jump into the longer explanation for those where maybe that short explanation isn't enough and you want to get more into the nitty-gritty of all the concepts involved in this. So in order to do that, let's do a quick review of our different types of potential energy. Because electrical potential energy is usually the type of energy that students are least familiar with. The type of potential energy that we're usually most familiar with is gravitational potential energy. Now, most of us know that our equation for gravitational potential energy is just going to be U equals mass times gravity times height. So what does this mean? Well, it means that if we take an object with a certain mass and we move it against the force of gravity, raise it to a certain height, for example, then we're doing work on that object when that happens, and we're going to store that work done as potential energy. So a classic example of this is hydroelectric power plants. Hydroelectric power plants, they take water and they store it at a higher elevation. And then, of course, that stored water that's stored against the force of gravity, it accumulates potential energy. And that potential energy can be used to then, when they release the water, power turbines. So that's gravitational potential energy. Notice that our H here is directly proportional with our potential energy. So the higher we raise a mass against the force of gravity, the greater potential energy we're going to get. Now, the other type of potential energy that students tend to be more familiar with is that of elastic energy, or the energy of a spring. So our equation for elastic potential energy is just going to be U equals 1/2 kx squared. Remember that k is just our spring constant, and x is going to be our displacement of our spring, the amount we either stretch it or compress it from its equilibrium baseline position. So notice again, just like gravitational potential energy, the greater our x is here, the greater our displacement is, the more we stretch or compress our spring, the greater our potential energy is. And a good example of this is jumping on a trampoline. When a person jumps on a trampoline, they're compressing the springs that are connected to the fabric of the trampoline. And then that energy of them jumping and compressing the springs gets stored in the trampoline. And then you can use that energy to then rebound the person upwards. So now to the type of potential energy that's relevant to this question, electrical potential energy. When we move electrically charged particles from a neutral position against a charge gradient, we're doing work. And we can store that work as electrical potential energy. And our equation for electrical potential energy is going to be U equals K times Q1 times Q2 divided by distance. In other words, K here is just a constant, and then Q1 and Q2 are the two charges that we're looking at, the work that's done on those charges, and then D is the distance between our charges. Now, notice that this equation looks very similar to our equation for Coulomb's law. So I want to show you really quick how you can derive this equation for electrical potential energy by combining our equation for work with our equation for the force experienced by two charges, or Coulomb's law. So first, starting with our equation for work, we know we said that work is just force applied over a distance. And then our electrical force, which is Coulomb's law, is going to be K, our constant, times the magnitude of our two charges, divided by the squared distance between the two charges. So notice we can plug this Fe, our electrical force, into our work equation here. And what are we going to get? Well, we're going to get work equals K times Q1 times Q2 divided by R squared times D. And in this case, we said D, the distance, is exactly the same as R. R in this case just represents the distance. So what's going to cancel out here? Well, one of our R's are going to cancel out here with that D in the numerator. So we're going to end up with work equals K times Q1 times Q2 divided by D. And in this case, the work done, we can replace the W here with a U, because this, like we saw up above, right? This is exactly the same as our equation for electrical potential energy. So being able to derive and combine equations like this and understand the relationships between equations is really going to give you a big boost on the MCAT. And an example of electrical potential energy is capacitors, which we talked about in the last passage a lot. Capacitors, we know they store electrical potential energy by separating charges on their two plates. One of the plates on the capacitor will accumulate a bunch of positive charges, and the other plate on the capacitor will accumulate an equal and opposite amount of negative charges. And then we just keep that energy there stored, and we can use it for things like to use a defibrillator when someone's heart stops beating. You can all of a sudden take those capacitor plates, place them on the person's chest, and release that potential energy to essentially shock them back to life. So getting back to this question in particular, we're thinking about which of our configurations that were shown in our answer choices represents the state of maximum potential energy. Well, notice something interesting here. Versus with our equation for gravity up here, we said that as we increase the height we raise a mass to, we're increasing our gravitational potential energy. And similarly with our elastic potential energy, when we increase the displacement of our spring, stretch it or compress it more, we're increasing our elastic potential energy. But here with our electrical potential energy, if we increase our D, our distance between our two charges, since in the denominator of our equation, the opposite thing is going to happen to our U, our potential energy. So in other words, if we increase the distance between our charges, we're going to decrease our potential energy. Now, this tends to confuse students a little bit because they think that then answer choice A and C, which represent the sea of electrons having moved quite a bit either to the left or to the right of our positive ions, would be wrong, because since those electrons have moved a greater distance, therefore they think that electric potential energy is decreasing. But that's not exactly the case. And why is that? Well, that might be the case if we were dealing with a single pair of electrons, but in this case, we're not dealing just with one electron and one positive ion, one Q1 and one Q2. We're dealing with a whole sea of electrons and a whole bunch of positive ions and the relationships between them. So even though that our potential energy might be decreasing as we increase that distance between our positive ions and our electrons, we have to sum up all the amounts, all the potential energies between all our pairs of electrons and all of our positive ions to get our total electrical potential energy. In other words, our U total here, you could think of as being the sum. Remember that symbol just represents the sum of all of our pairs of electrons and positive ions. So we'd have our K, our Q, I'll do QE for the charge of our electrons, QP for the charge of our positive ions, divided by D. And of course, that D is the distance between our electrons and our positive ions. So in other words, as we move our sea of electrons farther from our positive ions, even though the work done on a per charge pair basis might decrease, you're going to be doing more work overall because you have to do work on all the different charge pairs. And because you're doing more work, you're storing more potential energy. So that's why our configuration A and C that shows our sea of electrons either moving quite a bit to the left or to the right of our positive ions is going to represent our states of maximum potential energy, versus our configuration B, which shows our electrons just right on top of our positive ions in their sort of equilibrium state. In that case, we're not really doing work because work has to be force applied over a distance and our electrons haven't been displaced at all. So just as you could think of like with elastic potential energy, and if we don't stretch or compress our spring, we're not going to be able to do any work and we're not going to be storing any potential energy. So, important takeaway from this question is that sometimes what happens when you're thinking about a single pair of charges, like a single proton and a single electron, might be a little bit different from what happens when you're thinking about a whole sea of electrons and a sea of protons and all the different relationships between them. So, I hope this explanation gave you a deeper understanding of this question, and I hope it also gave you a good review of all the different types of potential energy, because you should have memorized the equation for work, the equation for gravitational, elastic, and electrical potential energy, understand what they are, and be able to plug into those equations and manipulate them for the MCAT. So if this helped, please drop a like and subscribe to my channel for more content like this.